How do these schematic diagrams of the working principles of Raman and FT at our devices help researchers understand how the technologies operate in tandem to provide complementary insights into the materials used in sodium-ion batteries? And how do they contribute to optimizing the electrochemical performance of the batteries? How do the schematic representations of these devices assist in guiding experimental setups and improving the interpretation of results obtained from in-situ optical measurements? How can the refinement of obtained patterns be used to analyze changes in lattice parameters, and what specific role does this process play in studying the intermediate phase transitions of electrode materials? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the refinement of these patterns reveal new structural information and intermediate transition state products that may not be captured by conventional XRD methods? How does the synchrotron XAFS technique enhance our ability to study the surrounding chemical environment of electrode materials? And what are the advantages of adjusting the X-ray energy to examine the redox state, local electronic structure, and neighboring coordination atoms of each element in the material? How does synchrotron XAFS contribute to a more detailed understanding of the material's behavior by allowing the study of individual elements separately? And what insights can this provide into the overall electrochemical performance? What does the three-dimensional reconstruction of electrode material particles reveal about important issues such as the stresses experienced by the material during cycling? And how can this technique help establish a relationship between electrode pulverization and cycle life? How does the ability to reconstruct the electrode material particles in 3D provide more intuitive observations, and why is this significant for optimizing the design and performance of sodium-ion batteries? In the context of in situ synchrotron electrochemical cells, what design considerations are essential to ensure conventional electrochemical performance while also reducing X-ray absorption by the optical window material? How do different in situ cell structures, such as button cells and soft pack cells, contribute to the effectiveness of synchrotron radiation studies, and why are these configurations chosen for the analysis? What materials are commonly used for the optical window in these in situ synchrotron cells, and how do materials like beryllium, polyamide Kapton film, and mylar film compare in terms of their ability to reduce X-ray absorption? How does the use of specific materials for the optical window impact the quality and accuracy of the synchrotron data, and what factors must be considered when selecting these materials?